Yeah, let us start. So welcome everyone to the first session of the NCTS Algebraic Geometry Seminar. Today we have Giacomo Mazzadini from Bonn, and he's going to talk about virtually abelian automorphism groups of K3 surfaces. So yeah, please start.
Yes, thank you. So let me just share my screen. So today I'm going to talk about automorphism groups of K3s, and feel free to stop me anytime to ask questions. You can see this, the screen, right?
Can see it.
Okay, perfect. Okay, so let me just say that this is joint work. So it's a couple of joint works. The first one would be Simon Brandhorst, and then for the second, more recent preprint, also Markus Kirschmer joined us. And I'm going to work over an algebraically closed field of arbitrary characteristic, but if you prefer, you can think about complex numbers. And indeed, at some point, I will use, for intuition, complex numbers, just to give a bit of idea how these automorphism groups act on dynamically on the points of these K3 surfaces. So the very general main question that we're interested in is, so we start with X, smooth projective variety. Then we can consider the group of its automorphisms. So for instance, if we're over C, it's just the group of biholomorphisms of the variety. And we're interested in how complicated this group is. And I put quotation marks in complicated because one here can give a lot of meanings to complicated. And of course, different meanings lead to very different questions. For me today, complicated will be whether this group is virtually abelian or not. And virtually simply means that this property, in this case abelian, holds for a finite index subgroup. So let me just write that a group is virtually abelian or something if there exists, let's say, a group G, if there exists a finite index subgroup H that is abelian. And in order to kind of motivate why we're interested in this sort of question, it's probably useful to look at what is called the Tits alternative. So this comes from a theorem of Tits of like middle of last century. He proved it for linear groups, for finitely generated linear groups. But basically, he proved that if one is in a certain specific class of groups, then we have two possibilities for the complexity of them. And I'll state his theorem in a more generalized version that is more useful for us. So I'll take X to be a smooth projective surface. And then there are two possibilities for the group of automorphisms of X. So either it is virtually abelian, or it contains a free non-abelian subgroup. And by a free, I mean like a free group, so a free product of groups. In this case, we want it to be non-abelian. So for instance, you can think of, for instance, I don't know, Z2 star Z2 star Z2. This, for instance, free and non-abelian. Be careful that if you only put two copies, then it is virtually abelian, so we don't want that. Or for instance, we consider Z star Z, or many other possible groups. And this is a great result because, so in this form, I think it was proved by Ghisatullin and Kanta. And this result is great because it gives some sort of dichotomy for automorphism groups of arbitrary smooth projective surfaces. It says that either it is almost abelian or it is extremely complicated. So complicated that it contains a free group, and kind of free groups are kind of the most complicated in some sense. So this sort of dichotomy gives us a way to classify the complexity of an automorphism group of a surface. And we're going to be interested in when a certain surface has an automorphism group in case 1 or in case 2. And to give like a bit of background why we're interested in K3s, let me just briefly recall what happens for the classification of algebraic surfaces. So now we focus on surfaces. So let X be a smooth projective surface. And then there's an important invariant, which I'm sure all of you know, which is the Kodaira dimension of X. So it's a number that it's either minus infinity, 0, 1, or 2, Kodaira dimension. And okay, like if you don't know what this is, it just measures the positivity of the canonical bundle of X. Okay, so it's some sort of two-dimensional generalization of the genus of a curve in some sense. And I'm going to write down like a small table. So here we have the Kodaira dimension. Here we have the possible surfaces, X, and here we have what the automorphism group looks like. So we have minus infinity, 0, 1, and 2. And I'll start from this side, from the right side, because it's kind of, for our purpose, it's the easiest one. If the Kodaira dimension is true, then we have surfaces of general type. And these are very complicated, but their automorphism group is finite. So very easy group. It doesn't get easier than this. Then we have Kodaira dimension 1. Here we have elliptic surfaces. I'll come back to elliptic fibrations in a bit, but maybe many of you already know what elliptic surfaces are. But the important thing that we would like to focus on in this case is that the automorphism group here, it's always virtually abelian. And there's a very precise reason for this, is that not only there's an elliptic fibration in this case, but there's a unique elliptic fibration. So the whole automorphism group is just basically consisting of translations along this elliptic fibration, and then translation groups of elliptic fibrations are just abelian. But I'll come back to this in a second. This is just to say that this side of the table consists of kind of the easy automorphism groups. The left-hand side is much more complicated. For instance, in Kodaira dimension minus infinity, we have, for instance, P2. We have things that are birational, 2P1 times a curve. And here the automorphism groups are pretty complicated. Already for P2, we have PGL3. These are a very complicated group. Then we can also study these other automorphism groups. These are complicated. And I'm not going to focus on this because they require very different methods from those. But let me just write, these are complicated. And these are easy. And then we have Kodaira dimension 0, which is kind of in between. And there are 4 types of surfaces of Kodaira dimension 0, which we can put in 2 classes. On the left-hand side, we have K3 surfaces, which I'll define in a second. On the right-hand side, we have abelian surfaces, which you probably know. They're just smooth projective surfaces that have a commutative group law. And we also have their quotients. That's not too important. Here we have the Enrico surfaces. Here we have bielliptic. It's not so important. But what I would like to say is that this Kodaira dimension 0 case is kind of an in-between case. So the automorphism group is sometimes virtually abelian, sometimes not. And so in a way, these are the surfaces for which understanding this Tits alternative is most interesting. Maybe not most interesting, but it's very interesting. Because indeed, they exhibit both behaviors. And our final goal for today is to understand which K3 surfaces have a virtually abelian automorphism group. And in order to state precisely our theorem, I'll need to be a bit more precise, and I'll need to give a bit of background on K3 surfaces, because we're going to present some sort of classification of K3 surfaces with a virtually abelian automorphism group. But first, I would like to introduce K3 surfaces properly and then present our result. So, are there any questions about this short introduction?
Yeah, can I ask maybe about this theorem, Tits alternative? What does it mean by free non-abelian group? Or why is this free product of the group with two elements free non-abelian?
This one?
It contains the free.
So by free, I just mean a free product of some groups. And non-abelian, I just mean, actually, I should be more precise, probably non-virtually abelian also here. It's better. Subgroup.
Okay.
So yeah, we really want a free group that is, I'm going to be imprecise, but really a free group, not that is like easier than that. So these two examples are kind of the two prototypical examples. So a lot of a free product of many copies of Z2, or many free copies, or free product of many copies of Z. These are kind of the examples that we have in mind.
Thank you.
Yeah, of course. Any other question? Okay, then I'm going to start with some basics on K3 surfaces, and I'm going to take the next 20 minutes maybe to present some basics. Maybe you already know these things. In that case, I apologize. But let's say that we fix notation, okay? So I'm going to start recalling the definition of a K3 surface, since they're going to be the main object today. So a smooth projective surface is a K3 surface if two conditions hold. So we want the canonical bundle to be trivial, so linearly equivalent to 0. And we also want H1 of XOX to be 0. Okay, so they are K-trivial, so they have trivial canonical bundle, and actually we see it in the table before. There are mainly two classes. Actually, there are exactly two classes of surfaces with trivial canonical bundle. We have K3s and abelian. The second property, so that the H1 is 0, just singles out K3 surfaces. So as an example, something that in every talk about K3 surfaces comes up, but what is the main example? The quartic surfaces in P3. So if you like equations, you can think of x0 to the 4 plus x1 to the 4 plus x2 to the 4 plus x3 to the 4 equals 0 inside P3. And this is going to be a K3 surface. We just need to check that it's smooth, but that's pretty easy. So it's a K3. And actually, it's a very special K3. But we're going to come back to quartic surfaces like throughout the talk. And a very, very important feature of K3 surfaces is that their geometry can be understood by looking at a relatively simple linear algebra object, which is the Picard group. So let me remind you that if we have any, this is a very general definition, like if we have any smooth projective variety, we can consider the Picard group of X. So this is the group of, if you want, linear equivalent classes of divisors. So it's something inside the H2, a second cohomology group H2Z. And but here we have a surface, dimension 2. So it's even better than that, because Now this H2xz, in the case of a K3 surface, it's torsion free. It's isomorphic to Z to the 22. So this is just a free abelian group in the case when X is a K3 surface. So maybe I should write X K3 from now on. And in particular, it's a surface. So we have a cup product on H2. So we have a map from H2xz times H2xz to H4, which is the cup product. Sometimes people call this the intersection product. And this is just Z. So this means that we have a bilinear product on this H2. And we have a lot of properties about this. We know a lot of properties about this bilinear product. It is non-degenerate. Non-degenerate simply means that there is no element that is orthogonal to everything else, right? In other words, if you write down the matrix of the bilinear product, it's invertible, okay? So it's non-degenerate, it's even. Even simply means that if we take a vector and we couple it with itself, I'm just going to use kind of the usual K3 surface notation. So I'm just to write down the product as a dot. V dot V is always an even number. And we also know its signature. So again, the signature of a bilinear product is pretty easy. We just tensor with R. If we tensor with R, every bilinear product can be diagonalized with a certain number of ones on the diagonal, certain number of minus ones. And we can check that there are 3 positive directions, 19 negative directions. So we know everything about this bilinear product. And notice that indeed 319, they add up to 22, which is the rank of this free abelian group. And there's a nice word that captures all these things. It's the word lattice. So for today, a lattice is going to be a free abelian group with a non-degenerate even. So even should not be added to the definition, but for me it's going to be even bilinear form. For instance, H2 of xz is a lattice. And of course, this lattice structure is inherited by the Picard group, which makes the Picard group into a Picard lattice. So pic of X with this bilinear form is a lattice. So again, it's non-degenerate, it's even, but the signature changes. And the signature of this is given by the Hodge index theorem that I'm sure you have all seen. Otherwise, just feel free to stop me and I'm going to talk about this. But the Hodge index theorem says that the signature of this lattice, let me call it L, is 1, rho minus 1. So rho is the rank of the Picard group. And the Hodge index theorem says that there's a unique positive direction. The positive direction is given, for instance, by a polarization of the surface. Any other direction is negative. Okay, so we call these sort of lattices that have signature 1, something hyperbolic. So this is a hyperbolic lattice. So if you have a little bit of familiarity with lattices, Euclidean lattices are those that are positive definite, and then the next possibility. So positive definite means that the signature is like something, 0. The second thing that can happen is something, 1. Okay, in this case, okay, you can take a minus, okay, and make it signature 1, something. So this is kind of the next case after Euclidean lattices, and they're called hyperbolic because they have a lot of connections to hyperbolic space, as we will see in a bit. So, okay, now we have this this gadget, this Picard lattice associated to the K3, and I'd like to explain a bit how much we can understand of the surface from this Picard lattice. So I'm going to give us some examples. So the first example that I'm going to give is, let's say that we have X, a quartic in P3, containing a line. So it's not only a quartic, but it also contains a line. So in the Picard group, for sure, there are two elements. There's going to be the hyperplane class that I denote by H. And there's a class of a line, L. And so this means that there's this two-dimensional, rank 2 sublattice of the Picard lattice. We would like to understand the intersection product over here. So we want to understand how much H squared is, how much H.L is, and how much L squared is. Okay, so H squared is pretty easy because we have the self-intersection of a hyperplane class. This is just the degree of the surface. So this is 4. Then we have a hyperplane, in this case, a plane intersected with a line. At how many points they intersect? Just 1. So this number is simply 1. And then finally, we want to understand the self-intersection of L. And this we need the genus formula. And for any k-trivial surface, the genus formula simply reads, let me write it here. Genus formula is that the genus of a smooth curve is going to be, maybe let me write it this way. So if we have C, let's say smooth curve, but we would need less. Just the C squared is 2 times the genus of C minus 2. So in this case, a line is a P1, so it's genus 0, so this is just minus 2. And so this means that we have a Z2 inside the Picard lattice, and the Z2 has intersection matrix 4, 1, 1, minus 2. Okay, so when I write a matrix for a lattice, I simply mean that I have chosen a basis. In this case, this is H and L is the basis, and then I write down the intersection product of the elements in this matrix, okay? So the second example that I like to give is what happens when we have an elliptic K3. And probably I should at least try to define what an elliptic K3 is. And I'm going to be a bit sloppy and just define an elliptic surface for K3 surfaces. So let's say we have X a K3 surface. We say that it's elliptic if it meets a proper flat morphism, so a fibration, to P1. Okay, so here we are using the fact that we have a K3 surface because the base could be any curve, but for K3s it must be P1. And then the fibers of these fibrations are smooth. The generic fiber is a smooth projective curve, a smooth projective elliptic curve. But of course, there might be singular fibers. So let's say we can have a nodal fiber here. We could have a cuspidal fiber here. And we could even have more complicated fibers. Sorry. But let me just draw this for now. So an elliptic fibration is just a map to P1 whose fibers are generically smooth elliptic curves. And another notion that we will use is the notion of sections. So a section is simply a curve that I'll denote here with S0. So a smooth curve that meets every fiber of the fibration at one point. Okay, so this is the intersection point. And note that since we have a section, so we have a curve that meets every fiber at one point, we can equivalently define this as a morphism back from P1 that kind of commutes, that kind of is kind of an inverse of the fibration. So we have that, so I'm going to mess up the order, but we have that sigma and then pi is the identity. Okay, so we go back from P1, we have this curve S0, and when we map back, we have exactly an isomorphism, we have the identity. So this means that this is S0 is isomorphic to the base curve, which is P1. So I'm going to call this a section. And since we have elliptic curves as fibers, each fiber has a group law. So this means that now, whenever we have another section, let me draw it with another color. So let's say now we have another section here, S. Now we can do operations on sections, because let's say this is one section and then we have another section here, S prime. We can do operations between these two sections because on each smooth fiber, we have 2 points here. Let's say on this fiber here, F. We have an origin, 0, and we have 2 points, let's say P1 and P2. And every elliptic curve has a group law, so we can do P1 plus P2 is going to be a certain other point. Let's say this one. This is going to be P3, which is P1 times plus P2. So on each smooth fiber, we can do the sum of the intersection points of two sections. And if we do this for all fibers, we can see that we can define a group law on the group of sections. So we can define S plus S prime to be, by definition, the section such that on smooth fibers, the intersection point, let me call this one a second. A second intersected with a smooth fiber is the sum of S intersected F and S prime intersected F. And then, of course, this can only be defined for the smooth fibers, but then we just close it, right? Because most fibers are smooth. So this makes the group of sections that we usually denote with the Mordell-Weil group of sections. So we denote it with the Mordell-Weil group of the fibration, which is pi. This is the group of sections. And it's pretty easily an abelian group. Sorry. Because the group law on elliptic curves is abelian. Okay. So any questions about this? Maybe you already knew all of this, but is there any question? Okay, so let's go back to an elliptic case. Yeah.
Sorry, some basic questions. So do sections always exist?
Yeah, no, they don't. Sometimes they do, but there are some cases in which there's no section. Actually, maybe I could give an example in a second. And then it's a bit hard with terminology because it depends what people mean with elliptic fibration, if they assume the existence of a section or not. I don't. So for me, an elliptic surface is any map to P1 whose fibers are generically elliptic curves. But yeah.
Okay.
Yeah. Any other question? Yeah.
So if a elliptic K3 surface doesn't have any section, then there are fewer automorphisms. Or is it easier that case? Or
so it depends. I would say that it's more complicated because we'll see in a second that having a section imposes a strong condition on the Picard lattice that makes it kind of easier to study. Instead, when you don't have section, you have what we call multi-section. So curves that not only meet fibers at more than one point, but there's not a group law for those. So then it becomes a bit harder to study automorphisms in that case. But that's kind of what generically happens. Yeah.
Okay, thank you.
Of course. So let's go back to elliptic K3s, and since as we were saying, let's assume that there's a section. So I'll draw a easier picture since we have way too much stuff on the right. So we have here, our elliptic fibration. Maybe we have some singular fibers, and we also have a section. Let's call the section S0, and let's call the fiber F. So now we have two classes in the Picard lattice, at least. We have the class of F, and we have the class of S0. And these will lie inside the Picard lattice. And again, we want to understand the intersection matrix of this form. So we want to understand F squared, F dot S0, and S0 squared. And again, we can use the genus formula. So f is a smooth elliptic curve, so genus 1. So the square is twice the genus minus 2. Since the genus is 1, this is just 0. S0 is a P1, so again, the square is minus 2. And the intersection number is 1, because they meet at 1 point. So this means here that the intersection matrix for this lattice here of rank 2 is 0, 1, 1, minus 2. And it has a great advantage that this matrix has determinant, minus 1, but the absolute value of the determinant is 1. So we call this with a special name, we call it the hyperbolic plane, U. And it's one of the most important lattices, hyperbolic lattices. And yeah, it has this great advantage that it has determinant 1, which makes things slightly easier in many cases. I will see in a second. Okay, so these are the two examples of how we compute the Picard lattice of a K3 surface. And as I was saying before, we can really obtain a lot of strong geometric properties of the K3 by looking at the Picard lattice. And I can explain a second how this works. So let's see if I can find. So yeah, for instance, no, that makes sense. First, I need to explain something. So before I go back to this example that I had in mind, let me give a definition/proposition. Because in order to go from information about the Picard lattice to the geometry, we need to define what basically the Neff cone is, which again, you probably know, but let me just, since we're in the first part of the talk, let me just explain a couple of basic things. So if we have a vector of norm minus 2 in the Picard lattice, we call this a root. And we have seen just before that P1s on K3 surfaces have square minus 2. Okay, so kind of intuitively, roots correspond to smooth rational curves on K3 surfaces. Okay, so intuitively, minus 2 roots correspond to smooth rational curves. And then, as soon as we have what a root is, we can define what it means to be Neff in the special case of a K3 surface. It's even easier than normal. So remember that a vector V in PIC is said to be Neff if it meets, so it intersects non-negatively all effective curves, right? But it turns out that on K3s, it's even easier than that. We just need to check that the intersection number is non-negative against the smooth rational curves. So if and only if V times R is greater or equal than 0 for every R plus of a smooth rational curve. So in this sense, smooth rational curves, or equivalently minus 2 roots, control the shape of the Neff cone of a K3 surface. And this is actually equivalent to, more lattice theoretically, to V dot R is greater or equal than 0 for every R effective minus 2 roots. And very briefly, what do I mean by effective? Well, geometrically, it just means that it represents a curve. Because of course, if we have, by Riemann-Roch, if we have a vector of norm minus 2, we can check that it's either effective or anti-effective. So we just have to declare when it's effective. And we can do this in many ways. For instance, we could fix once and for all A an ample vector once and for all in PIC. And say, well, a root, it's either effective or anti-effective, and it's effective when A dot R is positive. Okay, so we have this ample vector, and we can basically partition a set of roots into the effective roots and the anti-effective roots, and this alone allows us to define what an F vector is on this K3 surface. And the third property that I would like to mention is that if we have an F isotropic, and isotropic simply means that it's of square 0, and primitive vector, primitive simply means that it's not divisible in the Picard group, right? We cannot divide it by an integer. This is called a cusp. And geometrically, this corresponds to elliptic fibrations, because Riemann-Roch tells us that such a vector induces a pencil of curves, and not only that, induces a pencil of curves of genus 1 by the genus formula. So cusps correspond to elliptic fibrations on X. So this is quite fun. So we have, in a way, translated the property of being a smooth rational curve into being a vector of norm -2 in the Picard lattice. And we have translated the property of having an elliptic fibration to being a vector of norm 0, which is also Neff and primitive, in the Picard lattice. And this is enough to give the following example. So let's go back to our first example of quartics in P3 with a line. So let's assume that X is a K3 with Picard lattice equal to 4, 1, 1, -2. So by this, I mean it has rank 2, and this is the intersection form. Recall that this is exactly the same matrix that we found before over here. So quartics with a line over here. And we can notice the following thing. Okay, sorry, it's very difficult to move. Sorry. Okay, so we can notice the following thing. So let's call again H the hyperplane class and L the line. We can notice that if we do H minus L squared, this is 0. It is just a simple computation. And not only that, so this means that this vector, let me call it E, is isotropic. Well, for sure it's primitive because, okay, the coefficients are 1. And it's also Neff. Why is it Neff? Well, we need to check all the effective roots, but it's, yeah?
Is E effective?
So E is effective because so E has square 0, so it's again by Riemann-Roch is either effective or anti-effective, and this H is ample. So we just need to notice that each dot E is how much is it? 3. So it's positive. So this means it's effective. Yes, thank you. So, but we can also say that it's effective because we will see in a second that it's Neff, right? Everything Neff on K3's surfaces is also effective. And notice that it's Neff because a simple computation shows that L is the only vector of norm -2. It's the only effective vector of square -2. So Neffness can just be checked by computing the intersection number with L. And E dot L is what? Is 3, right? 1 plus 2. So it's positive. So we have an isotropic primitive Neff vector. This means that E corresponds to an elliptic fibration. And why is this fun? Because geometrically, I'm not able to draw a picture, but geometrically, if we have this quartic with a line, we can consider the pencil of planes containing the line. And okay, we have a line, the residual curve is a cubic, degree 3. And not only that, it's a plane cubic, so it's an elliptic curve. So this means that if we consider the pencil of planes containing the line, we obtain an elliptic vibration on the K3 surface. But we obtain this geometric information purely in a lattice theoretical way by noticing that this vector has norm 0. So if we are in a very complicated geometric situation in which it's hard to keep track about every subcycle, every cycle, every curve that is on the K3, lattice theory just tells us, well, just look for vectors of norm 0, which is very easy to do, for instance, with a computer. And, well, you figure out the elliptic vibrations that way. So in this way, numerical properties of the lattice come back and help us understand the geometry of the K3 surface in a very, very effective way. Okay. So other questions about this example? Okay. So the last thing that I would
this
like to...
elliptic vibration has a section?
It does not.
Oh.
It does not because, yeah, that's a great question. Thanks. Because I said that I would mention it, but we noticed that if we change basis, and now we have the basis EL, we have matrix 0, 3, 3, minus 2. So this has determinant -9. Instead, we said that if we had a section, we would have determinant 1 over here, at least if we have rank 2, right? And in this case, we do have rank 2 by assumption, but determinant is -9. So no section. We have a trisection. So because the line meets the elliptic curve, so the plane cubic at 3 points, right? But thanks. It's a good observation. Okay, so another thing, the last thing that I want to mention about the basics of K3s is that this Picard lattice also allows us to compute the automorphism group of the K3, which is where we want to go to. So, and we do the following thing. So it's called, okay, it has several names, but I'll call it the global Torelli. It's a consequence of global Torelli, but let me just say that it's global Torelli. So there's a map from the automorphism group of X to the group of isometries of the Picard lattice. This is pretty easy. We take an automorphism F, and we associate the action of F onto the Picard lattice. Okay, it preserves the Picard lattice, it induces an action, and of course it preserves the intersection form because it's an automorphism. And not only that, this is a positive isometry. And I'll be more precise in a second about what this means. It's simply an index 2 subgroup because we don't want minus the identity here, right? No automorphism will induce minus identity on the Picard lattice, right? But you're free to ignore this plus for a second. I'll come back to this. And it turns out that this map is almost injective, so it has a finite kernel. But it has huge co-kernel. And the reason is that there are too many isometries of the Picard lattice. If we have an automorphism, the induced isometry must preserve the Neff cone. So if we do something a tiny bit smarter, and maybe let me just move this, and we consider here isometries. So maybe let me type phi in O plus such that phi preserves the Neff cone inside, let's say, pic of X tensor R. So the Neff cone is simply the set of all Neff elements inside pic. Then it turns out that this map has finite kernel and co-kernel. And another important thing is that this group on the right has the advantage of being a purely lattice theoretical object. And I'll say it in a more precise way. It works as follows. So if we have the group of isometries of the Picard lattice, we can consider a very special normal subgroup of it. It's called the Weyl subgroup. And it's the subgroup generated by all reflections into -2 roots. So it works as follows. So we start with a vector R. of square minus 2, so a root. And then we can consider the following isometry as R from peak of x to peak of x. That takes a vector and gives back v plus v dot r r. So one can check that this is an isometry, and it has a very precise reason why this is called a reflection, because if you just look at reflections in R to the n, they have a very similar structure. You can see that, for instance, if you plug R to SR, we get minus R. So locally around R, we have the hyperplane R orthogonal, and R is 10 to minus R. So that's why it's called reflection. And I'll come back to this subgroup in like 5 minutes. But this Weyl subgroup is defined as the subgroup generated by all these SR. And a refined version of global Torelli says that this group on the right, so the group of isometries that preserve the Neff cone, it's isomorphic to the quotient O plus of pic divided by the Weyl subgroup. And now really this object here is purely lattice theoretical. Like, we're not talking about K3, we're not talking about an F anymore. We're just considering isometries of a hyperbolic lattice divided by the Weyl subgroup, which is defined in terms of the minus 2 roots. And so a super important consequence of this is that up to a finite group, because this map could have finite kernel and co-kernel, the group out of X only depends on its Picard lattice. And so now I'm able to rephrase our original question of saying which K3s have a virtually abelian automorphism group into a more refined question that is which Picard lattices of K3 surfaces lead to a virtually abelian automorphism group. Because of course, this finite group here does not change the fact that a group is virtually abelian, right? Virtually is literally up to a finite group, right? So I can rephrase our goal. That is, for which Picard lattices pic of X does X have a virtually abelian automorphism group? Okay, so are there any questions about these basics about K3s? Okay, again, feel free to stop me anytime, but now the goal is to go to hyperbolic geometry and to see how this translation from geometry to hyperbolic geometry of the lattice will yield super strong consequences for the automorphism group of K3s. So maybe let me call it hyperbolic geometry. So this part is going to be a bit more sketchy. It's going to be a lot of pictures. So stop me if I say something that doesn't make a lot of sense. So we start with an arbitrary L hyperbolic lattice. Remember that hyperbolic lattice simply has signature 1 rho minus 1. And for us, it's going to be the Picard lattice of a K3 for simplicity. Then we can take the tensor product L tensor R. And over here, we can consider the hyperboloid v dot v equals 1. So let's try to draw a picture. So we have the cone of vectors of norm 0. This sometimes is called the light cone. And then inside, we have the vectors of norm 1. This is a hyperboloid, so it's very close to here. And it goes here, like this. Of course, these are cones. And here we are in R3. And again, these vectors, of course, if a vector has norm 1, also minus v has norm 1. So there are two sheets of this hyperboloid. Let's choose one. Let's choose this one above, and we call this HL. So this is called hyperbolic space. And this is a very nice space. It's kind of, of the non-Euclidean geometries, there's spherical geometry and hyperbolic geometry. Hyperbolic geometry is this one, in which we look at in this case, the surface, and the geometry of it is such that straight lines between points are lines that line to hyperplanes through the vertex. So for instance, in this case, now it's going to look very bad, but if you imagine that I have 2 points here, then I can take the plane containing these 2 points and the vertex and intersect it with the hyperboloid. So we obtain maybe something like this. Okay. So yeah, you have to imagine that. It's not going to look pretty, but like this thing. If we intersect the hyperbolic with this plane through these 3 points, we're going to obtain a segment like this. And this is a straight line in this geometry. And this is kind of a cool geometry. It's a bit hard to visualize. So people use the following trick. So, and maybe let's give a name. This is called the model of the conformal. So the conformal model, and it works as follows. We take this point here, which is the point 0, 0, 0, minus 1. And then we take each point on the hyperboloid, let's say this one, and we connect it to this point here. And on the plane last coordinate equal to 0, we'll intersect it at a certain point here. And if we do this for each point on the hyperboloid, or maybe this meets it here, we're going to obtain the disk. Okay. So if we project this segment, we obtain something like this. Okay. So now we have this model of hyperbolic space, which is a ball with a sort of weird geometry on it. So I'm going to draw it like a bigger picture here of the ball. So this is again HL, and we have these 2 points here, and the quotation mark straight line between them is something like this. It looks curved, but it's straight in this geometry. It's the shortest path between these 2 points. And there's another advantage of this picture, which is if you look at the light cone, so this one here, these are the vectors of norm 0. If you imagine that we go, let's say, very far away, this light cone is in a way tangent to the hyperboloid. So if you imagine that we project a very far away point on the light cone to this point here, this 0, 0, 0, minus 1, okay, this picture looks terrible, but so probably the disk would look something like this. Makes more sense now. If we project this, no. Okay. If we project this point on the light cone, it will end up tangent, so on the boundary of this ball. So in a way, we can interpret the point on this boundary as projections of the vector of norm 0. So the boundary parametrizes vectors of norm 0 in PIC tensor R. While vectors inside parameterize vectors of norm 1, or up to scaling vectors of positive norm. Okay. So, and now we'll see how this picture why this picture is so useful. So I'll draw another picture. So hopefully it's a bit more clear. So we start with our hyperbolic space. And this is basically the whole of peak of x tensor R. Right? It's like basically vectors of norm 1 over here. But we're interested in a subcone of this. We're interested in the Neff cone. And in order to compute the Neff cone, if you remember, we need to take the vectors that have non-negative intersection with all -2 roots. So let's take, for instance, R a -2 root. And we look at the hyperplane R orthogonal, which is going to look something like this. So this is the subset of vectors that intersect R with multiplicity 0. So these are orthogonal to R. So there were going to be one side, which are the vectors that meet it negatively, let's say this side, and a side where it's going to meet it positively. And again, R is not only a -2 root, but it's an effective -2 root, right? So it's a positive one. And if you imagine that we do this for all the roots, we're going to obtain some sort of tessellation of this hyperbolic plane. I have no idea how it's going to look like, but maybe it's something like this, and maybe we have a root here, and then maybe here we have an accumulation point, and so on. Then maybe we have another root here. Like, I'm not sure how it's going to look like, but at the very end, if we take this chamber here inside, this is going to be the Neff cone. And I denote it sometimes with DL because it's in terms of the hyperbolic lattice L. This is the Neff cone because by the drawing really means that this is the set of vectors that have positive or non-negative intersection with all the -2 roots. Okay. And if you remember, we have this map from the automorphism group of the K3 to the automorphism group of the Neff cone. So the isometries that preserve the Neff cone. And if you remember, this was equivalent, this was isomorphic to the group of isometries quotient out by the Weyl subgroup of reflection. And now we can see this really in action, because if we take this -2 root here, this R here, corresponding to this hyperplane here, we can consider the reflection, and the reflection really sends a vector V here to something here. So, you know, we can see that this reflection SR sends the chamber Neff of X into this chamber here of vectors that have intersection positive with all roots except for R. In that case, it's negative. And you can imagine that if you apply now the reflection with respect to this wall, you end up to another chamber, and so on and so forth. Yeah? Is there a question? Okay. If there's a question, please stop me, but I can't hear anything. So what I mean is that, yeah?
I think there's no question, but maybe somebody online doesn't have the mic muted. I'm not sure. But yeah, I think we can go on. Thanks.
Okay, perfect. Thank you. Thank you. So you can see that by applying reflections through walls, we can just change chambers. So this group W acts, maybe let me write in black. So this group W acts transitively on the set of chambers. Chambers are just kind of these connected components after removing the walls. And so now this isomorphism, I hope it's clear, because whenever we have a space and we have a transitive action, then the fundamental domain, in this case the Neff cone, is just, so the set of isometries that preserve this domain, the fundamental domain is just the quotient by the group that acts transitively. Right? So this is kind of a proof of this isomorphism in terms of hyperbolic geometry. And the advantage that we have now, that we have rephrased everything in terms of hyperbolic geometry, is that we can use hyperbolic geometry. And I'm going to recall the three main types of transformations of hyperbolic space. So there are three types of isometries of hyperbolic space. So the first type is elliptic isometries. Elliptic isometries are those that fix a point in the interior of HL. So I'm going to write this circle on top, I mean the interior. So I'm not considering boundary points now. Elliptic ones are those that fix a point inside hyperbolic space. Then we have parabolic isometries. So these are, of course, not elliptic first, and they fix a unique point on the boundary. So a unique vector of norm 0. And then finally, we have hyperbolic isometries, which could be defined as, well, those that are not elliptic nor parabolic, but we can be more precise. Though these are those that fix precisely 2 points on the boundary. So hyperbolic space is kind of easy enough object that its isometries can, yeah, sorry? Okay, I guess there's a no question again, but again, feel free to stop me. So hyperbolic space is such an easy linear algebra object. There are just 3 types of transformations. And they look like this: elliptic, parabolic, and hyperbolic. And I can draw a picture of how their dynamics look like. So maybe I can do, let me try to do a picture here. So here we have elliptic type. Here we have parabolic type and hyperbolic. So in the case of elliptic isometry, we have a fixed point inside. And then around this point, the dynamics look like a rotation around this point. So what I'm drawing as kind of the flow lines of points around this fixed point, they look like we're rotating around this point. Okay, so pretty easy isometry. And it turns out that in our case, these elliptic isometries always have finite order. So these are periodic isometries. And then we have the parabolic ones. So first of all, parabolic are not elliptic, so they have infinite order, but by definition, they fix a unique point on the boundary. So let's say they fix this point. And then how do the flow lines look like around this point? They look like what we call horospheres. So something like this. Around this point. And in this case, the order is infinite. And then we have hyperbolic ones. Hyperbolic ones have 2 fixed points. So if a transformation fixes 2 points, it must also fix the geodesic between them, so the straight line between them. So it will fix this line over here. And how does the flow lines look like? Well, these lines is fixed, and the points are sent exponentially fast from this point here, that is some sort of, how do you call, like the sink of the dynamical system, that send it to here, that is kind of the hole or the attractor of the dynamical system. So points are sent from very close to here to very close to here. And around these points, the dynamics look something like this. So these again are the flow lines of the system. Sorry. So also in this case, we have infinite order. And in order to distinguish between parabolic and hyperbolic isometries in a neat way, there's an invariant that we can associate to the isometry, which is called the dynamical degree. It's simply defined as lambda. So this is the spectral radius of the isometry. So this is an isometry, so we can write it down as a matrix. The spectral radius of a matrix is simply the maximum norm of an eigenvalue. Okay, so maybe I can write it down. So maximum norm of an eigen. Of course, the eigenvalues are complex numbers, so we cannot say the maximum eigenvalue. We have to take the maximum norm of an eigenvalue. And when we have defined the spectral radius, now we can distinguish between parabolic and hyperbolic transformations, because parabolic ones have only roots of unity as eigenvalues. So the spectral radius is 1. While in the hyperbolic case, the spectral radius is bigger than 1. And we can see exactly here why, because the points around the sink are sent away from it. So here the eigenvalue at this point, that is a fixed point, is going to be bigger than 1, while this over here is an attractor. So the eigenvalue corresponding to this fixed point is going to be less than 1. Okay, but again, we're taking the maximum norm, so this one is going to count, the one that is bigger than 1. Okay, so this is hyperbolic geometry. But how can we come back to K3 surfaces?
Sorry, I have a question. So,
yes,
so
of course.
in the hyperbolic case, I guess all the flows should converge to one of these fixed points.
Yes.
Right.
Yes. Yeah, that's a good point. So maybe the picture is not precise. Maybe let's do it like this. So first it's going to look like, so I would like to say that first the points here, they go a bit like this, and then they go towards the other one. Look better now? Like, it's very hard to draw the flow lines in this case. I just want to say that points that are very close to the sink are going to end up very far away from it very fast. This is what I mean. So exponentially fast away from it. And then they go exponentially fast towards the attractor. Yeah, but thank you. So maybe here, something like this. Thank you. So let's try to go back to K3 surfaces. And I want to keep this slide kind of close, because then I want to draw kind of the equivalent, the picture for K3 surfaces. So remember that we have a map from the automorphism group of the K3 surface to the automorphism group of the Neff cone, sending F to the induced action on the Neff cone. And now we have here 3 possibilities for F star. It's either elliptic, parabolic, or hyperbolic. So what does it mean for F? So how do we come back to K3 surfaces? Well, let's do it. So the first case is the elliptic case. In this case, we have finite order. So, well, it's pretty easy dynamics on the K3. Every orbit is periodic. Okay, so we have a point. So orbits are finite. Then we have the second case, in which we have a parabolic element. So let's remember what this means. This means that there's a unique vector on the boundary that is fixed. But now, vectors on the boundary are isotropic. They have norm 0. And they are Neff because we're looking just at automorphisms that preserve the Neff cone. So this means that on the boundary, we're fixing an F isotropic and primitive vector. So we're preserving an elliptic fibration. So in this case, the K3 has an elliptic fibration. And the flow lines of the automorphism are, well, to be absolutely precise, they can have a finite action on the base. So we have this point here. So there could be a finite action of the automorphism on the base. That's not too important. But up to removing this finite order action on the base, the flow lines are just, they follow the elliptic lines, the elliptic curves. So this means that, maybe let me move this. Here. So in this case, many orbits are going to be infinite. But they're never going to be Zariski dense. Because every point, if we start in an elliptic fiber, we're going to remain on it. Okay, we could go to some other elliptic curve, but just finitely many. So the orbits of points under this automorphism will never be dense. And then we have the third case, in which we are neither elliptic nor parabolic, and here the dynamics are going to be really hard to draw. So the dynamics are complicated and chaotic. So I don't know, draw something like this. This is a chaotic dynamics. And in particular, we can prove that there are many Zariski dense orbits. So this trichotomy of hyperbolic transformations really translates into a trichotomy of automorphisms of the K3 surface. We have elliptic ones that are periodic and so finite orbits. We have parabolic ones in which the orbits are infinite but never dense. And then we have Zariski dense orbits. And another important invariant that we can associate to this, it's called the entropy of the automorphism. It's called entropy. It's simply defined as the logarithm of the lambda defined above. So in the case of parabolic transformations, it's 0 here. So we call this automorphism sometimes of 0 entropy. And in this case, the h is bigger than 0, because log of number bigger than 1 is bigger than 0. And we call this of positive entropy. Okay. Are there questions about this? Okay, so I just have the last 15 minutes, so it's time to finally state our main result. But now we have kind of all the tools to do that. And maybe the last notation or definition that I would like to give is the following. Again, it's a definition / a theorem. So if we have any subgroup of isometries of hyperbolic space, then first thing is that G is virtually abelian if and only if G is elementary, which means that it has a finite orbit. In HL. And more importantly, there are 3 types of elementary groups. So there are 3 types of virtually abelian groups of isometries. So 3 types of elementary groups. And again, there are 3 types, 1 for each type of isometry. So there's the elliptic type, Okay, these are just finite groups. Nothing very interesting here. Then there's the parabolic type. And the elementary groups of parabolic types, they all contain parabolic elements, but not only that, they all fix the same boundary point. Okay, so this is an infinite group, but each parabolic element fixes the same boundary point. And then we have an elementary group of hyperbolic type. And in this case, this is a kind of peculiar group. It's always virtually cyclic. So virtually cyclic, it means that it contains a finite index subgroup that is isomorphic to Z. And not only this, but, so this is finite index, but this Z is generated by a hyperbolic transformation. So this is a super strong result in, but it's also some sort of basic result in hyperbolic geometry that tells us that if we want a virtually abelian group of isometries, we only have 3 types. Either it's finite, or it's infinite, all of each fixing the same boundary point, or it's virtually cyclic, generated by a hyperbolic transformation. And now we're really ready to state our theorem. So I have to owe this to many people because the work started with Nikulin and Wimberg in the 80s. And then there was the result of Chunyu in 2022. And then there's Brandhorst and me, and also Kirchner in the new one. And so this is 22 and 25. And basically what we have, it's a complete classification of Picard lattices of K3 surfaces with a virtually abelian group. So let me state like this. So let X be a K3 surface. So the first part, let me call it part 0, is that if the Picard rank of X, so this is the rank of the Picard group, is less or equal than 2, then the automorphism group is virtually abelian. Okay, this is pretty easy and known for a long time. Because in this case, the lattice is so small that there's not much going on. So the interesting part starts when the rank is at least 3. And if the rank is at least 3, then what we say is that there exist exactly 359 Picard lattices of K3s with virtually abelian automorphism group. And I can be much more precise than this, because again, there are only 3 types of virtually abelian groups. There are those of elliptic types, so finite automorphism group. These were classified by Nikulin and Wimberg, and there are 118 lattices. And the rank is at most 19. Then we have the parabolic ones. So parabolic elementary automorphism group, which sometimes are called zero entropy K3s. These were classified by us and Chunyu at the same time, and there are 193 lattices. And then in the last work, we finally completed this classification by classifying those hyperbolic elementary automorphism group. Turns out there are 48 lattices here. And it's probably also relevant that the parabolic ones happen until rank 18, and the hyperbolic ones, actually, they happen only until rank 4. So quite interesting. They only exist for very low rank of the Picard lattice. So this result gives a complete classification of K3s with a virtually abelian automorphism group. And not only that, it specifies what type of elementary group they are in each case. So other questions about this main result? Okay, so maybe
sorry,
I'll
just a
use-
quick
yeah.
question.
Yeah,
Are
sure.
these up to isometry or
Yes,
are they?
absolutely.
Okay,
So if the Picard lattice is isometric to one of these 30, yeah, absolutely, yes.
I see. Okay, thank you.
Thank you. Yeah. So maybe I should add that the automorphism group, we said at some point, up to a finite group, it really only depends on the isometry class of the Picard lattice. So this is a virtual abelian if and only if the lattice is isometric to one of these lattices. Yeah, thank you. So maybe 2 words about the proof. So I don't have time to explain it. I should say that part of it's computer assisted, because we can use a lot of geometry to basically pin down the possible lattices to a manageable amount. But unfortunately, manageable is still too much for a human. So we kind of create lists, and then we let the computer check them. So, I mean, if you're interested in this, it's actually also the computer assisted part is really interesting if you're interested, of course, in this sort of things. So feel free to ask me questions. But maybe in these last 5 minutes, I would like to give a couple of examples, because I think also these examples contain some of the geometric intuition and the geometric ideas that we apply to prove this theorem. So let's come back to our original example. So quartics in P3 with a line. So remember, these K3s have Picard lattice, or at least the very general ones, have Picard lattice 4, 1, 1, minus 2. So how can we compute the automorphism group? So we want to compute the isometries that preserve the Neff cone. But here it's pretty easy, because if you remember, I said that this is the only minus 2 root. Okay, the only effective minus 2 root. So if there's only one effective minus 2 root, the whole automorphism group must preserve it. Okay, so out of X preserves the line. But then if it preserves the line, then it also must preserve the hyperplane class, because there's no other class of square 4 that meets the line at one point, right? And so out of X acts trivially on the Picard group. And so out of X is finite. Okay, so pretty easy in this case. The automorphism group of these K3s is always finite. Let's consider, for instance, a more complicated quartic in P3. And this is an example that was studied by Cayley, I think around the 1850s. And sometimes people call this Cayley's determinantal quartic. Determinantal quartic. It can be described again as some determinant of some nice matrix. It's a really, really nice description of a quartic. Lattice theoretically, its Picard lattice is as follows. So it's 4, 2, 2 minus 4. And so this looks very different from before, because, for instance, you can notice that the numbers on the diagonal are multiples of 4, and the numbers outside are multiples of 2. So here, for sure, there's no root. Every norm is going to be a multiple of 4. So there's no vectors of norm minus 2. And so this means that the automorphism group has this map to the isometry of Pic. And here we would have to divide by W, but there's no root. So this map is basically an isomorphism up to a finite group. And so now it's just a lattice theoretic problem of computing this isometry group, and it's not too hard to prove that this is isomorphic to Z, generated by a hyperbolic transformation. So this means that the automorphism group is virtually abelian of hyperbolic type. And this is something that already Cayley knew. He was very surprised to find a quartic in P3 with an automorphism of infinite order, because you might know that if you consider surfaces of any degree in P3, and actually this works for hypersurfaces in general, their automorphism group is almost always finite. It can only be infinite in two cases, plane cubics and space quartics. So this was a huge discovery, and this example is still relevant today. In our terminology, we call this a virtually abelian automorphism group of hyperbolic type. And then maybe the last example that I can give, it's an example where the automorphism group is not virtually abelian. And I could consider for this a quartic in P3 containing two disjoint lines. Okay, so even more special than before. So let's see what is the Picard lattice now. So we have the hyperplane class, then we have the two lines of square minus 2. They both meet the hyperplane class at one point, and they're disjoint. So the Picard lattice, at least in a very general case, will look like this. Okay, so I claim that out of X is not virtually abelian. And let me try to give a very, very quick proof of why this is not virtually abelian. And this is kind of the strategy where we handle most of our cases in the proof of our main theorem. So the first observation is, so this is the hyperplane class, this is the first line, and this is the second line. We saw at the beginning that if we consider H minus L1, we obtain an elliptic vibration. Okay, remember that these, in the other case, these had no section, right? But in this case, it has a section because H minus L1 times L2 is 1. So this means that this is an elliptic vibration with a section, and actually we can check that it has infinitely many sections. Same thing for the second line. Nothing changes. H minus L2 is again another elliptic vibration. Now L1 is a section. And not only that, it has infinitely many sections. So now we're in this situation in which we have, let me call this one E1 and this E2. We have two elliptic vibrations with infinitely many sections. So the Mordell-Weil group of each of the two vibrations is infinite. Remember, this is the group of sections of the elliptic vibration. So these two groups are infinite. So I can take in here an element of infinite order. And what I mean by this is I consider the translation by a non-torsion element in the Mordell-Weil group. So the picture looks like this. So I have the elliptic vibration. I have the zero section, and I pick a section of it that is non-torsion, such that this point is non-torsion, and then I translate by this point. So this point is going to send to this point is going to send to this point, translating by the intersection point of S with the fiber. And now what I obtain is that these two elements both have infinite order, and they're both parabolic because they fix an elliptic vibration. Remember that fixing an elliptic vibration means they're both parabolic elements. But if I consider the subgroup of the automorphisms generated by F1 and F2, how can these, let's assume that by contradiction, the automorphism group is virtually abelian, so it's elementary. Let's see, it cannot be this subgroup here, it cannot be elementary of elliptic type because it's infinite. It cannot be elementary of parabolic type because in that case, all elements would fix the same boundary points. but we're fixing different boundary points. Once we're fixing E1 and once we're fixing E2. Yeah? Okay. And I'll conclude in a second. So it cannot be elementary of elliptic type. It cannot be elliptic of parabolic type. It can also be cannot be elementary of hyperbolic type, because in that case it would be virtually cyclic. While in this case we have two elements that do not commute, so it cannot be Z. And so this means that this subgroup cannot be elementary. And so the automorphism group is not virtually abelian. And I think with this, I should stop. Thanks a lot for the attention, and feel free to ask questions if you have.
Okay, yeah. Thank you for the talk. Is there any question?
Yeah. So yeah, just a question about the main theorem. I'm just wondering, so in the list of automorphisms that you turn up, so are they all pairwise not isometric? It's like the 118, for example, those are 118 distinct isometry classes.
Absolutely. Yes. Pairwise not isometric. Exactly. Yes.
Okay. So how do you come up with this list to begin with? Do you start with a larger list and then partition it into isometry classes, or do you use like Nikulins invariants or something along those lines?
I can give you maybe some ideas in the case of the classification of the parabolic ones. So the parabolic ones, we are basically preserving an elliptic fibration. And in order to make things a bit easier, let's assume that we preserve an elliptic fibration with a section, right? Then in that case, we have a copy of the hyperbolic plane inside U. Okay. And general theory of lattices tells us that this induces a splitting of the Picard lattice as the hyperbolic plane plus something negative definite. And now we use, so this last example that I gave should give the indication that if we want to be virtually abelian, there can only be one elliptic fibration with infinitely many sections, right? Because if we have two, we can consider this subgroup, and this is not going to be elementary. So this translates in lattice theoretical terms into this W being, we call it unique in its genus. Again, like I could, it's not that hard, just that it's not worth explaining exactly what it is. But let me just say that there's a complete classification of lattices unique in their genera. So at this point, we just take this enormous list, and we just let the computer check all cases. And what the computer does, taking any lattice, comes up with the isometries that preserve the Neff cone, and we check whether this group is virtually abelian. If it is, we keep it on our list, otherwise we discard it. And in a way, this is kind of the easiest example. When we don't have a section, it's much more complicated than this, and we need some more refined geometry, hyperbolic geometry tricks. But this is kind of the general idea. We kind of use geometry to reduce to a certain list that is known, and then we just ask the computer. Yeah, very, very roughly.
So you classify the orthogonal complement of the embedding, and then how do you enumerate like what possible genera can occur for that?
Yes, yeah, exactly.
I mean, so are there lists for if you have the signature of that negative definite part that you can just find all of the possible genera that occur?
The thing is that being unique in its genus is a very, very special property. There's a finite explicit list of negative definite lattices that are unique in their genus. So for our list of virtually abelian automorphism group, the Picard lattice is going to look like U plus a lattice in this finite list. So that's why we can ask the computer, because we already have kind of a finite list already. There's a caveat there, but let me just say for now that it's finite.
Okay, perfect. Thank you.
Thank you.
Are there any more questions?
A quick question, maybe how big is this list of the W's? Out of curiosity.
I don't exactly remember, but for sure it's a different order of magnitude than 359. Might be, I think, either in the thousands or maybe the tens of thousands.
I see.
Something like
Okay.
that. Yeah.
Okay, nice.
The main, maybe let me just say that the main problem is that we have to consider this lattice as unique in their genus, and then we could multiply them by an integer. So we can consider also lattices that are obtained by this by multiplying the intersection form by an integer. So the list is not finite anymore, it becomes infinite, and then again we have to do reduction steps. But I think the final list of things that we check with the computer is in the thousands, and we only obtain something in the hundreds, something like that.
I
Yeah.
see. Thanks.
You've kind of answered this question, but I mean, so can you just say a little bit more about how the Picard rank of the K3 surface relates to the virtual abelian condition? Like, if you
Yeah.
specify the Picard rank, can you enumerate all of the virtual abelian lattices?
Yes. So I can do this for high Picard rank because there are fewer examples. For instance, so if one works over C, the Picard rank is at most 20. So for instance, let's say if the Picard rank is 20, turns out that the automorphism group is never virtually abelian. This is not too hard to show even without our hard computations. If the rho is 19, there's only one example. This was found by Nikulin. There's the lattice U plus E8 plus E8 plus A1, if you know what that is, otherwise not too important. And this is finite automorphism group. And from rank 18 on, the situation becomes a lot more interesting, because now there's going to be some finite automorphism groups. I think there's one example here. I don't remember exactly. I think there's one example. And I think there's a parabolic elementary. I think there are two examples. And going down, there are going to be more and more examples. But just to say that the bigger the Picard rank, the rarer virtually abelian automorphism groups happen. And yeah, I don't know if that answers your questions.
Yeah, no, that's great. Thanks.
Thank you for the question.
So any more questions? Yeah, I actually have some questions. So do you actually consider fixing a polarization vector, or?
So if you fix a polarization vectors, you're fixing an element of positive square. So you're fixing an element inside the hyperbolic space, so you're going to have finite order. So if you want to have infinite order, you're not going to fix any polarizations. This is kind of a tricky thing.
I see. Thank you.
Yeah.
Yeah, and also like at the beginning of the talk, you kind of like classify the Kodara dimension 0 surfaces into abelian surfaces and K3 surfaces, and then like Enriquez surfaces are also kind of belong to the K3 surfaces. So if your K3 surface has a covers an Enriquez surface, so can you say anything about the automorphism group for that Enriquez surface? Like
yes, I can say, I mean, I would be happy to say something. So we have a different work. This is together with Gebhard Martin and Davide Veniani, in which we ask the same question, virtual abelian automorphism groups of Enriquez surfaces. And I can summarize what happens. So let's take X a K3, and let's take Y the Enriquez quotient. So it turns out it's a pretty fascinating result. So clearly, if the automorphism group of X is virtually abelian, then the automorphism group of Y is going to be virtually abelian. Because this is the canonical cover. So if maybe you can prove the contrapositive, if this is not an elementary, then also this is not going to be elementary because it's kind of a subgroup. Okay. The fascinating thing is that we prove that some sort of converse, that if the automorphism group of Y is infinite and virtually abelian, then also the automorphism group of X is virtually abelian. And this happens for a unique family of Enriquez surfaces. A unique two-dimensional family. The Enriquez surfaces, so we have the Enriquez side and the K3 side for this two-dimensional family. On the Enriquez side, they were studied by Barth and Peters. And they have kind of an interesting geometry. From the side of K3s, they are K3s with Picard lattice equal to, There are those with Picard lattice U plus E8 plus D8, if I'm not mistaken. So this is actually one of the two, when I was saying Picard rank 18, there are two examples in the parabolic elementary. This is one of the two. And these are the only K3s that cover an Enriquez surface, and they have a virtually abelian automorphism group. So there's a unique two-dimensional family of K3s with this property, which is sort of surprising, I guess. But yeah, so this is what happens for Enriquez.
Right. So this is also, I think there is a paper by Alice Galvanati and maybe other people on this K3 surfaces and Enriquez surface. Is that right, or is it a different?
Yeah. I mean, there's a lot of like one can say a lot about this these surfaces. For instance, if I'm not mistaken, these K3s also admit symplectic involution. So one can also study this K3 surface from a point of view of symplectic involutions. They're also super interesting. They're kind of they are super well studied, and it was interesting for us to do the classification and to see that this is the only family. So it is special in some sense, and yeah, it has been studied many, many times.
Right. Yeah. Thank you.
Yeah. Thank you.
A quick question about this. So is there examples of out Y being finite and the other thing not being, or we just don't know?
Yes, actually, this is another thing that I could say is that if the automorphism group of the Enriquez is finite, then the automorphism group of the K3 cover is not virtually abelian.
Oh, I see.
It's very strange.
Okay, I see. Thanks.
But I don't have a good reason why this is the case. I know that this is the case because maybe intuitively, when we have an Enriquez surface with finite automorphism group, the K3 cover is very, very special. Usually has Picard rank 20. So it cannot have a virtually abelian automorphism group. So yeah, it's a very, very different behavior when it's finite. Yeah.
Yeah. So any final questions or comments? If not, then let's thank Giacomo again.
Thank you a lot.